We're going to do some example rotational momentum problems. So in this first one, we have a diver who can reduce her moment of inertia, which is another way of saying rotational inertia, by a factor of 3.5 when changing from the straight position to the tuck position. So straight position is straight body like a pencil, tuck position is all balled up. If she makes 2.0 rotations in 1.5 seconds when in the tuck position, what is her angular speed in revolutions per second when in the straight position? So we know that momentum must be conserved, right? So first let's write out the things that we know. We know that the moment of inertia in the straight position is equal to 3.5 times the moment of inertia in the tuck position. We also know that the angular velocity in the tuck position is equal to 2 revolutions or rotations in 1.5 seconds. So that gives us 1.33 revolutions per second. And we know that momentum has to be conserved. So the momentum, angular momentum of the tuck position is equal to the angular momentum of the straight position. And angular momentum is I times omega, so the rotational inertia of the tuck position times the angular velocity of the tuck position equals the rotational inertia of the straight position times the angular velocity of the straight position. And then we can plug in some numbers. So moment of inertia of the tuck position, or rotational inertia of the tuck position, times the omega of the tuck position is 1.33 revolutions per second. And then I'm going to plug in 3.5 times IT in for the rotational inertia of the straight position. So 3.5 IT times omega of the straight position. So we can see that our rotational inertias of the tuck position cancel out, and then we can just solve for angular velocity of the tuck position, which is 1.33 revolutions per second over 3.5, and that gives us 0.38 revolutions per second. And that should make sense that the angular velocity decreased because the rotational inertia increased. And when you multiply them together, they have to be the same value as in the beginning. So there's one example. Let's do one more. Now we have a potter's wheel, and it is rotating around a vertical axis through its center at a frequency of 1.5 revolutions per second. The wheel can be considered a uniform disc with a mass of 5 kilograms and a diameter of 0.4 meters. A potter throws a 2.6 kilogram chunk of clay approximately shaped as a sphere of radius 7 centimeters onto the center of the rotating wheel. What is the frequency of the wheel after the clay sticks to it? So this is a collision problem. Notice that they are sticking together. So anytime you have a collision where two things stick together, you should have a little flashing bulb go off in your brain that says this is an inelastic collision. And if you have an inelastic collision, you're going to use momentum to solve the problem. Usually. So we're going to think of momentum here. And let's lay out our notes. So the angular velocity of the wheel is equal to 1.5 revolutions per second. We know that the mass of the clay is equal to mass of the disc, mass of the wheel, sorry. The mass of the wheel is equal to 5 kilograms, and the radius of the wheel is equal to 0.2 meters because it says the diameter is 0.4. So I'm going to use these together, and we know that the moment of inertia of a disk, you may have to look it up, but it's 1/2 mr squared. So when we calculate that, we get 1/2 times 5 kilograms times 0.2 meters, and we square that, and that gives us a number that I amazingly don't have written down. Okay, so that gives us 0.1. I could have done that in my head if I looked at those numbers. 0.1 kilogram meters squared. So that's the moment of inertia of the wheel. And then we have the mass of the clay is equal to 2.6 kilograms. And the radius of the ball of clay is equal to 0.07 meters. And we're going to use I equals 2/5 mr squared for that one because this is a sphere. So you have to use a different moment of inertia equation or rotational inertia. So we have 2/5 times the mass, which is 2.6 kilograms, times the radius squared, and the radius is 0.07 meters. We're going to square that, and then we're going to get meters squared 0.0051 kilogram meters squared. Okay, so those are our moments of inertia. Now we are going to use conservation of angular momentum. So we know initial angular momentum is equal to final angular momentum. Initially, we just have the wheel spinning. So we have the moment of inertia of the wheel times the angular velocity of the wheel. And then at the end, we have the two stuck together. So just like in regular momentum, if you were to have two, let's say, train cars collide and stick together, you would just add their masses together because now they're stuck together. We're going to add their moments of inertia together. So we're going to have I of the wheel plus I of the clay times this final omega, which is what we're solving for. So we get omega final is equal to I of the wheel times omega of the wheel divided by I of the wheel plus I of the clay. So we can plug in numbers now. We have a moment of inertia of the wheel by itself was 0.1. Yeah, 0.1 kilograms times meters squared times the angular velocity, which is 1.5 revolutions per second. Now, you don't actually have to change to radians per second on these problems because you're just gonna, like, I'm solving for angular velocity, so whatever unit I have here is what's gonna be here. There are times, like when you're using torque, you have to be in angular, like radians per second or radians per second squared for acceleration, but for this one you don't have to change your unit. And then down here we have 0.1 kilogram meters per meters squared, excuse me, plus 0.0051 kilogram meters squared. And so you can calculate that out and you can get your new final angular momentum. And I just did it in variables on my paper and didn't notice, so let me calculate it really quickly. And so we get 1.43 revolutions per second. So it doesn't slow down much, but it does slow down a little bit. But we should kind of double check that we're getting a slower angular velocity, which makes sense because we have a higher moment of inertia now. All right, that's all.